Welcome to the third part of the presentation describing the RM software for filter design. It is related to CMAC, polynomial monotonic amplitude low-pass filters. CMAC stands for critical monotonic amplitude characteristic. After describing the idea of critical monotonicity and low-pass filter design, we will present four main classes of critical monotonic low-pass filters: least square monotonic, Hoppin, Butterworth, and at the end we will give some comparisons among them. When monotonic amplitude is considered, one in fact has in mind the critical monotonic amplitude characteristic, CMAC, of selective polynomial filters. The term critical means that the amplitude characteristic has maximum number of inflection points in the passband in which the derivative touches the zero while not changing its sign. Since the passband attenuation is always positive, one may state that this class of filter have complex attenuation zeros in the passband except for the origin. The position of the inflection points affect the behavior of the function, which means the asymptotic selectivity, the selectivity at the edge of the passband, the reflected power in the passband, and the flatness of the amplitude at the origin. According to these properties, four classes of CMAC filters were proposed in the literature. The RM software produces all four of them. We will start with the LSM filters, which stands for least squares monotonic. These are developed under the condition of minimum reflected power in the passband. As can be seen from the figure on the right, this class of filters has incomparably better amplitude characteristic in the passband in comparison with the rest. The second category is the so-called Hoppin or H-filters, which exhibit monotonic amplitude characteristic with maximum asymptotic selectivity. This means that at very high frequencies, this class of function will have the largest attenuation of all monotonic counterparts. The oldest critical monotonic characteristic is the Populus filter, which is often referred to as the L filters or optimal filters. Its main property is to have maximum slope of the amplitude characteristic at the edge of the passband. As can be seen from the figure on the right, it represents a transition between the H and the LSM filters. And finally, Butterworth. This is the oldest and the best known class of filters exhibiting monotonic amplitude characteristic. Its main property is that it is maximally flat at the origin, meaning that all the inflection points are located there. Apart from the simplicity of the transfer function synthesis, it has no advantages of any kind in comparison to its monotonic counterparts. And let's start a short comparison. As we here, the passband attenuation characteristic of CMAC filters of 7th order are presented, and we can see that the Hoppin filters introduce a large amount of attenuation in the passband, or a large amount of reflected power in the passband, while the LSM filters stand on the opposite side, exhibiting the lowest reflected power. The Papoulis filters are a kind of transition between the Hoppin and LSM, and Butterworth filters are some specific solution which is acceptable only from simplicity point of view. Here, the stop band characteristic is analyzed for the same set of functions. As we can see, the H and L filters, Hoppin and Papoulis, are competing each other in the sense that at the beginning, near the passband, the Papoulis filter are more selective, while at higher frequencies, H filters take over to become the most selective monotonic filters of all. The LSM filters stand in between these two and the Butterworth filter, which is incomparably less selective. And that would be the end of the short description of the critical monotonic amplitude characteristics. We will come back to this when comparing them with the so-called Chebyshev characteristic, and also we will come back when describing the methods of further improving the selectivity of these kind of filters. Thank you for the attention.